This is 2023 paper 1 question 4. So we're told that this number is a root of this equation. Find the value of p. So if it's a root, that means we can sub it in and the equation will be true. So that means that we'll have 1 plus I squared plus and then 3 minus 2i times z, which is 1 plus I, plus p will be equal to 0. And that's true because we're told that this is a root, or in other words, it's a solution. So we need to just solve for b. So when we square 1 plus I squared, we'll get 1 plus 2i plus I squared. That's just squaring out the bracket. Plus, then multiply these brackets, we'll get 3 plus 3i minus 2i minus 2i squared plus p equals 0. Okay, so 1 plus 2i, I squared is minus 1, so that's just minus 1, plus 3. 3i minus 2i is plus I, and then minus 2i squared, that's minus 2. Well, I'll say minus 2, and that's multiplied by minus 1, because that's what I squared is, plus p equals 0. Now we can just kind of collect like terms. So we'll have 1 minus 1, they cancel each other out. Then we'll have 3 plus 2. Again, that's because this will minus and minus makes positive. So we'll have 5 in total. Then you have 2i plus I over here. That'll give us 3i. And that's good. Plus p equals 0. Then bring them to the other side, and we get that p is equal to minus 5 minus 3i. And that's our answer in the form a plus bi, and a and b are integers. Then we're told to use De Moivre's theorem to find the values of w, for which w squared is this number. So in order to use that, we have to get this into polar form first. So we need to write minus 1 plus root 3i. So minus 1 goes this way and then up for the I-axis, because this is the imaginary axis, this is the real axis. So we're going to be roughly kind of, it'll be a little higher root 3, so it's like here. It's not very well drawn, but it doesn't really matter. So we have something like that, right? So what we need to know, of course, is we need to know this angle, and we also need to know the length of the complex number. So what we can do is we can figure out what the green angle is by looking at this right angle triangle. And then what we can do is we can do 180 minus that green will give us this red angle. And the reason we have to use the red angle is because it's kind of assumed in all the formulae that we measure from the positive real axis. So for the angle. So here's a right angle triangle. This is a distance of 1. This is a distance of root 3. And let's figure out what this angle here is. I'll call it alpha. So we can use tan. So tan of alpha will be equal to opposite, which is root 3, over adjacent, which is 1. Tan inverse on both sides, and then we get that alpha is equal to 60. And then we'll call the red angle here theta. So this means that theta has to be equal to 180 minus 60, which is 120 degrees. I'm just doing this in degrees because people generally tend to find it simpler. Now to find the hypotenuse, we know that 1 squared plus root 3 squared will be equal to whatever the hypotenuse is squared. We usually call it r. So 1 squared will end up getting 4 on this side because root 3 squared is 3. So 1 plus 3 is 4 equals r squared, which means that r is equal to 2 because r is a distance. So that means we can write it in polar form as r times cos theta plus I sine theta. If you find it, the one will, the formula should make sense. You can see where it comes from easily if you mess around a bit. But it's also in the formula and tables booklet under De Moivre's theorem. So you can see here we have the r times cos theta plus I sine theta. That's one way to remember it, but there's also a nice way to show that that's true using the triangle. But basically that means we're going to write our complex number, w squared. Instead of writing it as minus 1 plus root 3i, I'm going to write it as r, which is 2, multiplied by cos 120 plus I sine 120. And you can multiply that out and make sure that it's actually equal to this, just to double check if you'd like. So now what we can do is we can do both sides to the power of a half, and we can use De Moivre's theorem to do that. But in order to do that, of course, it says to give each value of w, values of w, so we need multiple values here. So the way that we can get multiple values is instead of saying cos of 120, remember that we can always add on 360 to an angle. So we can actually rewrite this as 2 times cos of 120 plus 360 times some number. I'll just call it m. I won't call it n because that might confuse you with the formula. Plus I sine of 120 plus 360m. And again, the reason I'm doing that is because now I can let m be different numbers and I'll get multiple solutions, whereas beforehand you can see here that's just one answer, whereas now I have multiple answers that I can use. So we can do both sides to the power of a half. So if we do both sides to the power of a half, so I'll do this to the half and this to the half. Then we can use De Moivre's theorem. So this is our kind of polar form to the power of a half. That's like this. So what we can do is put the power of a half just on the modulus, and then we can multiply the angles by a half. So that's how it works. So then w squared to the power of a half, that just gives us w will be equal to 2 to the power of a half, or the square root of 2, times cos, and then we're halving the angles. So we'll get 60 plus 180m plus I sine of 60 plus 180m. And we're going to look for two answers because we had w squared. So we can let m equal 0, and then we'll get that w is equal to the square root of 2 times cos 60 plus I sine 60. And then our other one will be m equals 1. You can use different numbers, but these are just two adjacent ones. That'll definitely work. So the square root of 2 times cos, and then if m is 1, we'll have 240 plus I sine 240. And we can just get numbers on both those. Does it say in the form a plus? Yeah, a plus bi, so we have to do that. So for this top one, what we'll end up getting is root 2 over 2 plus root 6 over 2i. That's just rationalizing the denominator. You might have 1 over root 2. And then the other one will be minus root 2 over 2 minus root 6 over 2i. And this should make sense because our thing was squared, right? So when we square this, you could also think about this. This is just for intuition. You've got the answers. These are the two answers. But in terms of intuition, this is the same. The second one is the same as minus 1 times root 2 over 2 plus root 6 over 2i, which is the same as this one, just multiplied by minus 1. And that makes sense because when we square this, the minus 1 will go away. And then we just have this squared, which is the same as squaring this. So that makes sense that these are our two solutions. Then we're given an Argand diagram, not that it matters for now, but we're told to write the complex numbers IU and the complement of IU in their simplest forms. IU is the complex conjugate. So IU will be equal to I times A plus BI, which will be equal to AI plus BI squared, which is equal to AI minus B, because I squared is just minus 1. And then usually we write it as minus B plus AI. That's just because we usually put the real part first. And then the conjugate of IU, so the conjugate of IU will be the conjugate of minus B plus AI. And the way that we get the conjugate is we just change the sign of the imaginary part. So we'll get minus B minus AI as the conjugate. So minus B minus AI, and there we go. Then we're told to plot them. So IU is minus B plus AI. So here we have A plus BI. So this is kind of complicated. So it will help if we look at the distances. So the real distance here is like this. That's A. And then I'll do in green, this is the distance B. So we have minus B. So that means we go minus B is roughly going to be like over here. And then plus AI, it's going to be like roughly here. You could use a ruler and kind of get measurements. But this is going to be IU. So that's because this distance B, but we're going horizontally, and then the distance A, we're going up. And then in terms of the conjugate, where it's just minus B minus AI. So instead of going up by A units, we're just going to go down by A units. So this here should be IU conjugate. And yeah, so they're the two plotted. Then we're told to state a transformation or transformations that would send U to the complement of IU. Don't use translation. So U is up here, and we want to go to IU. So what we could do, well, there's a very simple one, is we could just rotate it by 90 degrees. So if you imagine rotating this by 90 degrees over to there, it would end up there. I think that's kind of the most straightforward to say it. So let's just say a rotation of 90 degrees, and that's going to be counterclockwise. And we'll say about the origin. That's because the center point, if you think about drawing a circle, the center point of our rotation is going to be there. So it's going to be kind of like this, right? So it's important to say because, for example, if we were rotating it, it's important that you say about the origin. Because if we were rotating it, for example, about, let's just arbitrarily say, if we rotate it about this point, then as we're rotating it, it's going to kind of look like this. It's just going to be rotating around that point. So it's important that we say it's rotating about the origin, and it'll be rotating around like this. So, yep, that is an example of a transformation. Sorry, it says IU conjugate, so we actually have to, where we got to here with the 90 degree rotation, we actually have to get to here. So we have the 90 degrees counterclockwise, and then you could imagine if we mirror it along the real axis, so we could say, what word do they use to be axial symmetry? That's what it's called. So we can say, yeah, we can say axial symmetry through the real axis. So that just means that we're kind of doing axial symmetry vertically. I'm sure if you said like mirror, they'd be fine, but maybe they're looking, they can be a bit picky about the wording. So axial symmetry is the correct word you should use.